In this lesson, we're going to focus our attention on understanding parallel systems and working with threads and multi-threaded applications. And so before we get started, let's first take a look at or discuss what exactly do we mean by a parallel system. And so when we think about computing thus far, we've dealt with serial computing systems. And in that sense, we have software that executes based off of serial computation, meaning one step occurs one after the other in lockstep. And so we focused on having discrete steps of instructions that execute one after another. And this is based off of a single processor approach for execution. On the other hand, in parallel systems or parallel computing, we could think of being able to divide and conquer the approach to solving a problem. So within this case, we can have discrete components that are not executed sequentially, but instead are executed in parallel while one component is being processed, another component is being processed. And this allows for a quicker coordination of efforts to provide for a faster obtainment of results. And so let's break things down into a abstract sense, in the sense that we have a program, and a program is going to represent a static image or state that has been loaded into memory. Then we also have a process, and a process is going to just be a program in execution. And so when we think about this, we have a process is going to equal a program plus its states. And the state, of course, evolves as the program executes. And so when we talk about parallel systems, we introduce the concept of a thread. And so what exactly is a thread? Well, if you are considering a thread, you want to consider that we have a program that is executing. And within that program, we have various actors that are involved. And the program can have one thread that is being executed to complete a specific task or process that the program needs to accomplish. But then we can also have another thread that is executing to complete another portion of the program. So in general, we're able to have a program that has multiple threads that execute to control the state of the program. And so a thread is essentially a part of the process that is executing. And so we can define a process as being the program plus the state of all threads that are executing in the program. And so let's analyze how threads can be used in software. So let's take the case of a sequential process. In this example, we have a program that is executing serially, and that we have a portion of it that is compute, and then a portion of it that is input and output, and then another portion that is compute. But the portion that is compute does not necessarily require the results of the I/O process that has occurred previously. So what exactly could we do to speed up the program execution? And if you could consider that maybe we start at time 0 and the program ends at time 20 nanoseconds or so. We can create a multi-threaded or threaded approach to this program, in that we can have computation occurring while I/O is being processed. And by allowing for this to occur, we can execute the I/O portion of the program while the second compute portion is executing. This therefore reduces the execution time for the entire program. And so in this case, let's say this provides for a 20% reduction in the total execution time of the program. So in that case, we're able to identify specific tasks in a program that do not require sequential results to be obtained before executing. So this allows for us to provide for overlapping computations while the I/O activity is completing. And as we can see here, the multi-threaded approach would be the approach that would finish first over the sequential. And so let's consider another example of how we could make use of threads. And let's consider the approach of a video surveillance application. And in the video surveillance application, we have various tasks that need to complete during the program execution. And these tasks, we have a digitizer component that is used in the program, and the digitizer is used to convert the video into appropriate sequence of frames or pixels. We'll have a tracker component, and the tracker component is used to analyze each frame and identify any content that needs to be flagged. And then we also have a alarm component. And in this alarm component, we're able to denote if there is a action that has occurred that requires the attention of the user. And this can be alerted based off of the tracker. So the pipeline for this, the application resembles our traditional processor pipeline. And so in this case, we can consider that we could have multiple processors working together for the execution of this program. And in order to speed things up, we can have each portion executing in parallel. And so that provides us with a scenario of how you could make use of parallel systems for solving a problem. So the direction that we're going in is that we're going to understand how programming support for threads can be utilized. We'll provide for a high-level discussion on synchronization and communication between threads. And then we'll also discuss appropriate architecture and OS support that is required for threads as well. And so it's important to keep in mind that the usefulness of threads is that it provides the appropriate mechanism for creating appropriate parallel or concurrent programming techniques. And these can be controlled by utilizing a variety of programming specific functions. And so let's consider that we have a multi-threaded program. And in this program, we have appropriate main as well as subroutines or procedures. The thread will start executing in some top-level procedure of the program, and this is denoted by a command called thread create. Let's consider that the thread will terminate when main terminates or when the thread's top-level procedure terminates. And once the thread has terminate, we're going to need to provide for appropriate synchronization and communication among the threads to provide for the results that have been obtained. This provides for a basic workflow for working with threads. And so what exactly are some programming support that is available for us to create threads? Well, for creation, we have specific commands that are available, specifically thread create. This is a top level procedure call that will initialize the thread. We have appropriate mechanisms for determination of the thread. This involves the return, in which after the top level procedure ends, the thread will return to the calling function. And it can also be done by explicitly killing the thread. We have appropriate mechanisms that are in place that will allow for a thread to wait for other child threads to process. And then this can be provided together with thread join to bring the results together. For synchronization, we have appropriate mutex functions as well as condition variables that can be used as well. And so when we think about a thread executing, we can think of the flow of the program being that we'll have a main thread that occurs and thread create is called. Once the thread is created, it executes and the result is returned to the top level call of the thread. In this case, it would be foo that is returned. So let's consider that we have a program where we have a thread create and join example. And in this case, we have a function foo, and then we have our main function. We define appropriate variables of f and then a thread type called child TID. And this is the thread ID that is created. So child thread ID is going to be equal to our thread create, which calls foo. Once the program completes its appropriate process, we'll join the results with child of the thread ID. And so in this case, what occurs is that the program executes. We have thread create occurring. Foo is occurring while the program executes. The result gets returned, and then there's a join with the thread. We'll wait for the results to occur. We encounter the point where foo has completed, and then we'll join with the original parent thread. And so then the program will continue. So this represents the process that occurs as the threads execute. And so it's important to consider in this case that you can have a number of different threads that execute based on the characteristics of the hardware involved. Some processors can have 1 to various number of threads that occur, and additionally, GPUs can have thousands of threads that can execute at once. And so when we think of a thread, we want to think of it in what manner. Is a thread the same as a process? Usually part of a process, has nothing to do with the process, usually refers to a set of processes, is part of the memory hierarchy, or often involves a needle. And so we want to think of a thread as usually being part of a process. And so when we think of when a thread is going to start its execution, do we consider it starts its execution in main at some top level procedure that is part of the same program, at some top level procedure that is part of a different program, or none of the above? And as our previous example has shown, we want to think of a thread's execution as starting at some top level procedure that is part of the same program. And so when we consider the duration of a thread, we want to consider a thread lives forever. B, does a thread terminate only when the top level procedure where it started returns? C, a thread terminates only when main terminates. D, a thread terminates when either the top level procedure where it started or main returns. Or E, a thread terminates at the first context switch. And in this case, we want to consider that it will terminate when the top level procedure where it started returns. And so let's consider programming with threads. And there are a few things that we need to keep in mind when we're considering programming with threads. We want to consider the synchronization that is involved. And when we mean synchronization, we're talking about an appropriate coordination of the threads. And then we want to consider appropriate communication. In communication, what we mean is for inter-thread sharing of data. You want to consider that threads can be in different processors. And so what are some mechanisms that can be in place to achieve appropriate sharing of the data that is provided from threads? We can have software components that allow for the data sharing to occur. And this can be accomplished by keeping all threads in the same address space by the operating system. And then we have appropriate hardware mechanisms that are in place. And hardware mechanisms can be accomplished by shared memory and, of course, caches that can be utilized to provide for a shared addressing space. And typically, it's going to be a combination of support for both hardware and software that is going to be required. And so let's revisit the example that we previously introduced of our video producer consumer app. And if you recall, we have systems that operate in parallel, the digitizer, the tracker, and the alarm portions that are utilized. And so let's consider appropriate mechanisms that are in place for the digitizer and the tracker. And so the digitizer is going to represent the producer, and the tracker is going to represent the consumer. And so we'll have a circular buffer that is utilized, and each image is an array of pixels. And so let's denote that the head is going to be denoted, and it's going to represent the first valid field frame in our frame buff. And then the tail is going to be the first empty spot in our frame buffer. So this is represented as a circular buffer. And then we have appropriate buffer available. And so this is used to count the number of unused elements. So buff available can be calculated as equal to buff avail minus 1. And then the tail is going to equal to the tail plus 1 with regards to the digitizer. With regards to our tracker, we'll have bufferVal equal to bufferVal plus 1, and head is going to be equal to head plus 1. And so you want to keep in mind the tail is what is utilized by only the digitizer, and the head is utilized by only the tracker. Frame buff is going to be shared between both bufferVal and the frame buff. And so global variables that are involved are bufferVal as well as the frame buff that is used. And so let's consider the processes that are the program for each one of these components. We have our digitizer that is available that will process a type of image. And then we have our tracker that is available. Each one is making use of bufferVal to a certain extent. With the digitizer, we have a loop that executes based off of the condition that bufferVal is greater than 0. It grabs a digital image, it sets our frame buffer, and then it provides for increment of the tail. And then bufferVal is reset. With our tracker, it executes as long as buff available is less than our max. It sets, provides a setting for the image that is being tracked. It updates the head, and then bufferVal is set for it, and the image is then analyzed. And so what is going on between both of these two processes and what information is being shared? So we see that there's a sharing of resources that occur between the digitizer and tracker processes. And in this case, we have bufferVal is shared between the two. Frame buffer is shared between both of them, as well as bufferVal for updating. So what does this bring to mind? Does this provide for an issue or a problem that we need to consider? Essentially, if these two are executing in parallel, we're going to have some hazards that are going to occur because each one is providing updates as the program executes. And if they're executing in parallel, then we need to ensure that they're not manipulating data during execution, or another thread is not pulling the data while the program is while the data is being updated. And so we want to think about this in terms of, let's say that we have both threads that happen to be executing at the red arrows. And so with the tracker, it's going to set bufferVal to be bufferVal -1. The digitizer sets it to be bufferVal equals bufferVal +1. So we're loading the values into our R1, and then we're going to do an add I, and we can see at this point that they are providing for, they're executing at the same point. And so this presents an issue. So is buff avail going to be 7 or is it 9? It really should be 8, and so this would provide us with an incorrect result due to synchronization issues. But this is just one small issue that occurs in this scenario. So we need to figure out a way to resolve the synchronization issues with regards to the sharing of the data. And so in order for us to accomplish this, we can make use of appropriate synchronization primitives. And so in this case, we consider locks and unlock. And with this, these are available mechanisms that can allow for critical sections to be controlled. And so we want to think of a lock as being able, as a data abstraction with semantics that can declare a number of different locks for declared variables of the data type. And so when we have a lock, this means that only one thread can hold that particular lock at a time. So once a thread requires a lock, then other threads cannot get the same lock until the first thread releases it. So this allows for mutual exclusion among the threads and busy waiting versus blocking. So we can have pthread mutex trylock, which is a no blocking call. We can have it with a lock, which is a blocking call. And so this allows for, and we can have appropriate calls to unlock the thread too. And so the usage, typically you'll have mutex lock, which will represent a data structure. You'll have mutex lock, which is used to acquire a lock, and then mutex unlock, which is used to release it. And so when a program is executing, the operating system has no idea what you do in the critical section. And so the OS will guarantee that only one thread in the critical section can be used. And so we'll refer to this as a guarantee in OS and invariant. So we can use locks to fix the synchronization issue that we've previously had. And this is done by software inserts to lock and unlock for both the digitizer process as well as the tracker process. And so in this case, what we see is that if one thread is going to acquire the lock, then the calling thread will block it until it becomes free. And so this is going to represent the block state of a thread. And so taking this into consideration, we can use a mutex lock. In what manner? It allows for exactly one thread to acquire it at a time, allows any number of threads to acquire it at a time, allows a defined number of threads to acquire it at a time, or none of the above. And as we previously demonstrated, it allows for exactly one thread to acquire it at a time. And so let's consider our example with our locks. What problem might arise here with the critical section? Well, the problem is that the sections that we've defined are too coarse. And so it results in no concurrency. And so this means that there isn't going to be a performance improvement. And so what are some further improvements that we would need to make? Let's focus our attention on the buffer avail data. And so in this case, we can see that there isn't necessarily a need for a mutex here. So in this sense, what we need to do is further refine our solution with locks. And so in order to do this, we want to use appropriate constructs. So here we see that we could have a deadlock that occurs for the sharing of information. So what we want to do is ensure that we don't include a mutex by restructuring this code with a while loop. And so what would be the issue that arises due to this reconstruction? We want to ensure that if there isn't any synchronization, then there isn't any concurrency. So that's not going to have a performance improvement. So what are some appropriate ways in which we can ensure that frame buff is utilized effectively by checking buff avail? If we have too much waiting that occurs, then that's going to waste CPU cycles, and in some cases can result in degraded performance. So let's consider what we really want to happen. We want to consider that if frame buff is full, then that means the tracker is slow. So their slow digitizer is waiting for space in frame buff. The tracker should let digitizer know when it makes room in frame buff. If frame buff is empty, then that means the digitizer is slow. So the tracker is waiting for an image in frame buff. The digitizer should let the tracker know when it adds an image to frame buff. And so ensuring all of these constraints would allow for us to stop the busy waiting that could occur. And so in our previous program, we have to consider the effect that the while statement has on our digitizer code. And so what we want to do now is add a condition variable. And so with the condition variable, we're going to provide for a way to abstract the semantics of the program to execute for a specific condition. So condition variables, we have pthread condition wait, which is a block for a signal. We have pre-thread condition signal, and it signals one waiting thread. pthread condition broadcast signals all waiting threads. And so some of the semantics for the invariants, we have pthread condition wait with the condition variable in mutex, and this will atomically release mutex m, and it puts thread to sleep on the waiting on a signal to condition variable C. And it will automatically relock mutex m on awakening. And so let's consider that we have 3 threads, T1 to T3, that all wait on condition var C. So what happens is in the OS is we'll have the condition for T1, which will wait until T2, and then to T3. So we want to wake up one thread waiting on condition variable C, and then the thread will then go on to reclaim its mutex before proceeding. And so now T2 can execute. And so, but what exactly are we waiting for with respect to the digitizer and tracker? We want to consider that the digitizer waits for frame buff to be not full, and the tracker is waiting for frame buff to not be empty. And so let's consider how we can incorporate wait and signal semantics into our digitizer and tracker programs. So essentially what we want is for each thread to enable the appropriate condition to allow for a deadlock not to occur. So with each thread, we're going to each thread will perform and while holding the mutual exclusion lock. So what we want to do in a good sense is ensure that the appropriate condition holds true so that we don't have any miscalculations in our program. So in this case, we want to keep the invariant maintained by making thread condition wait call. And so this invariant is calling the thread that is holding a lock. And so once complete, it'll be released the lock will be released on behalf of the calling thread. So this will allow for the thread to resume execution, and it'll reestablish the invariant. And so let's consider with respect to T1 and T2, T1 has a lock and then a critical section and then a unlock. T2 has a lock, a critical section, and then a unlock as well. How is this executed with regards to time? We have both T1 and T2 executing. T1 gets the lock, and so then T2 is going to be stuck. We have our critical section with regards to T1 executing, and then T1 unlocks, and T2 gets the lock, so the critical section for T2 can execute, and then T2 unlocks. So let's consider what is T1 doing during this time that the critical section for T2 is executing. It'll continue with its execution. And so exactly one thread at a time is given a critical section for this invariant. So what is the critical section in play? If we have threads T3 and T4, we'll notice that T1 and T2 has, in comparison to T3 and T4, have different locks. And so what this means is that we're able to have those threads execute at the same time. And so this OS invariant, we have exactly one thread at a time in a given critical section, but different mutex locks create different critical sections. But still at most, one thread can run in each lock. And so let's recall our condition variables for T1 and T2. We have our lock, and if not, we'll have our condition wait, and then our predicate is set to false, and then it will unlock. And then with T2, it'll send the signal if it's true, and then it'll unlock. So T1 gets the lock M. T1 then with condition wait will block. The OS releases lock M, and then T2 is able to get lock M. T1 is ready to run. T2 unlocks. The OS gets lock M on T1's behalf. T1 runs. And so the OS ensures that T1 gets lock M back. And so we need to make sure that the pred is set to true. And so how is this, whose responsibility is it to ensure this occurs? And that's going to be the programmer. So this is the logic that has to come into place when developing applications for threads and parallel systems. So back to our surveillance app. What exactly were we waiting for? We had to wait for the digitizer is waiting for frame buff to be not full. And so our predicate is buff avail doesn't equal to 0. The tracker needs to wait for frame buff to be not empty. And this means that the predicate is going to be buff avail does not equal max. So in this case, we need two condition variables. We have buff not empty and buff not full. And we know how to test for these conditions using the predicates. And so this provides us with a concurrency solution in that we want to ensure that we have appropriate checking for the value that in buff avail. And so in this case, let's analyze the invariants that are involved once we've inserted our condition variables in. So with our digitizer, we have our condition variables of of buff not full that is executed during our thread, that is utilized during our thread condition wait. And so it's important to keep in mind that for our invariant in this case is only one thread at a time in critical section, while buff avail doesn't equal 0. With our tracker, we're going to use our condition variable buff not empty, and only one thread at a time in the critical section, while buff avail doesn't equal to 0. And so in each one, we're able to use the thread condition wait call. And so the invariant is calling the thread. The invariant in this case is calling the thread holding a lock. So once executed, the library will release the lock on behalf of that calling thread. And so now let's consider, with regards to thread 1 and thread 2, exactly how many code blocks are in our critical sections here. We see that there is one in T1, and then we have another in T2. But there is a third as well. And this is where the programmer has to come into play to understand. And for this case, we have a third critical section that is hiding in T1. And so with regards to our condition wait, we need to consider that we have a lock M, and that is going to execute if the predicate is not true. Then we're going to unlock M. Then we need to wait until C is signaled. Then we lock M back, and then we set the predicate to false. And so this is important because, and after the predicate is set to false, we unlock. And so the predicate can change even though this block is a single critical section. And so that becomes an issue that can affect appropriate implementation details in parallels programming. And so we need to understand appropriate conditions for the shared resources. So what we want to ensure is that, considering the while loop that is occurring, we want to make sure that T1 enables the condition that T2 is waiting on. And so we need to ensure that we have a recheck for those invariants. And so in a recheck, we want to check the predicate and ensure that our initial condition has been satisfied for the program. And so upon rechecking, we want to ensure that we're able to continue the program and not have any synchronization issues that occur. So in this case, we've introduced a number of different approaches to handle synchronization issues in multi-threaded programming applications.